We've made it halfway through the course. At this point, we're going to set aside the calculus techniques that we've learned and focus on a new topic, Unit 6, vectors. The definition that we're going to use for vectors will be a quantity that has both magnitude and direction. To give ourselves a little bit of intuition about what this will mean, let's talk about an example. If you were to tell me that you're going to travel 5 kilometers per hour, you would not have specified a direction. In order to make this a vector, if you told me that you're going 5 kilometers an hour east, this would now be considered a vector. Let's take a look at how we could represent a quantity like this graphically. If we were to take a look here at vector A, and the notation that we're going to use is a variable with an arrow over the top will signify a vector. In this case, I've specified the magnitude or length of A to be 10 and the direction to be 30. As I mentioned before, speed, or the 5 kilometers an hour portion, was not a vector on its own. This would be considered a scalar. Scalars and vectors interact by stretching or compressing a vector. For instance here, 2a, or the scalar 2 times the vector a, interacts with a in a way that we would double the length of a but keep the direction constant. Negative scalars have another effect on vectors. If we have a negative scalar, or negative a, we would keep the vector the same length but draw it in the exact opposite direction. Another important thing to know is that it doesn't matter where you draw a vector, as long as you don't change the magnitude or direction, they will be equivalent. For example here, we have a magnitude of 10 and an angle of 30. If I pick that vector up and move it down, as long as I keep the direction and the magnitude the same, they will be equivalent. We will also want to get used to switching between an algebraic and graphical representation of vectors. In order to do this, we're going to make use of trigonometry that we've known since grade 9 or 10. Using what we know about right-angled triangles, if we think about this vector as a combination of a y component and an x component, we can represent it using the cosine to find x. X is equal to cos 30, and the y component being 10 sine 30. Typically, we will write this in this form. Our vector a variable with an arrow over top, being written as an ordered pair. What this ordered pair specifies is actually the end point of the vector when drawn between that point and the origin. We'll notice here, however, that there's a common factor of 5. We can actually common factor that portion out and rewrite this as a scalar times a vector. In this case, 5 would be our scalar portion, and root 3, 1 would be our vector portion. Let's take a look at how we can algebraically deal with vectors. If we're given the vector a, which is 2, 1, and the vector b, which is 2, 0, so again, what this means is that a has an x component of 1 and a y component of 2, and b has an x component of 2 and no y component. If we want to add these two vectors together graphically, the way we would do that is we would draw a and b head to tail, and the resultant, or the answer, a plus b, would be drawn from where you start to where you finish. If we wanted to figure out the direction and magnitude of r, we would do so using trigonometric techniques like sine law and cosine law. Similarly, if we wanted to do a minus b, we could do it in a similar fashion. If I was to draw vector a, I could think about it as adding the negative of b. So I would take b, flip the direction to get negative b, and my resultant would run from where I start to where I finish. Alternatively, we can treat this slightly differently. If I draw vector a and draw vector b such that they're tail to tail, the resultant would be drawn from the end of b, the vector being subtracted, to the tip of vector a. You can see here graphically that both of these resultants are the same. Algebraically, adding and subtracting vectors tend to be much easier. If we take vector a, or 2, 1, and vector b, 2, 0, and add them together, in order to find the resultant, we would add the x components and add the y components to get 3, 2. And you can see graphically, this looks correct. Similarly, subtraction works the same way. If we subtract the x components and subtract the y components, we can again solve for the resultant algebraically. Finally, when we're specifying direction, we're going to use a variety of methods in this course. First of all, we're going to use our standard angle system. and this would be how we've specified angles since the beginning of grade 11. We'll specify x as being 0 degrees, and we'll measure our angles going counterclockwise. A directional representation we will use will be, first you will specify a starting point, so in this case north, and you'll specify towards which direction you're measuring. So in this example, north 30 degrees east, we would see that as we start at north and we move 30 degrees towards east. The final way that we'll use to measure angles in this course will be a bearing system. We always start with north as being 0 degrees and we measure our angles counterclockwise. It will be good to get comfortable using all three of these systems as they will be used interchangeably throughout your homework. Next, let's take a look at an example of where we can apply these ideas. Suppose we have a plane flying at 250 kilometers per hour in a direction of north 65 degrees east. Now the plane is being pushed by a wind, a northwestern wind, and we want to figure out what the resulting speed of the direction of the plane will be. So the first place we should start for any problem like this is a diagram. So here we can see we've drawn in the vector v, the velocity of the plane, with a length of 250 degrees, or a magnitude of 250 degrees, in a direction of starting at north 65 degrees towards east. Next, we can also draw in the vector for the wind. We knew that it was specified from north, going west 55 degrees, with a length or magnitude of 75. Now it's important to remember that I can take a vector and move it anywhere I want as long as I don't change the length or direction. So we're going to do that here. We're going to take the wind vector and I'm going to place it at the end of the velocity vector. Why? Because if we know that if we're trying to find the resultant or the combination of these two, in order to do this graphically, we're going to join them head to tail, and the resultant or the answer will be running from where you start to where you finish. We now know that we've drawn a non-right angle triangle here. In order to solve this, we're going to use sine law and cosine law techniques that we've known from previous courses. At this point, though, we'll recognize that we don't have enough information to solve this. Let's go ahead and find some missing pieces. In order to solve this, we need to find some angles. We were given angles between north and our velocity vector and north and our wind vector, but we need to solve for an angle within this triangle. In order to do that, we can recognize that this is in fact a parallelogram. The velocity vectors that I've drawn in are parallel, as well as these wind vectors are parallel. So that means that if we add these two vectors together, we can use what we know about angles in a parallelogram, that they need to add up to 180, and subtracting the combination gives us 60. We also know that in a parallelogram, these two angles need to be equal. That means that this angle is also 60. We now have enough information to use cosine law. We have two known sides, or two known side lengths, and the angle contained between the two. So setting up this formula, we can now use the length, r, this side in the triangle that we're looking for, is now going to be equal to the cosine law formula we have here. Working through the algebra, we can now determine that the length of r is 242.2 kilometers per hour. But we're not finished. We know that in order to state our answer, we need both a length and a direction. We've determined the length. So let's take a look at our diagram again. Where is the direction that we're interested in? The direction that we're interested in will be theta here, the measure from north. The angle that we can easily find, however, is alpha. It's the angle within this triangle. First, solving for alpha, we can use sine law. Setting up our sine law and working through the algebra, we find that alpha is 15.5 degrees. So let's take a step back. How are alpha and theta related? Well, if we know that it's 65 degrees up until the velocity vector, and alpha is 15.5 degrees, then theta must be the subtraction of the two. So 65 minus 15.5 yields an angle of 49.5, and this tells us that we now know both the angle and direction. We can state our final answer. The speed and direction of the plane will be 242.2 kilometers per hour at an angle or direction north 42.9 degrees east. We'll see many more examples of this in our homework. Good luck.